Is it on?
I think so. Can you check like from your phone? Or something?
Okay. My channel.
We have to disconnect the Wi-Fi. Let's see what I wanted. Okay, yeah, it's working.
It's on? Is it?
Yeah, and
What
it's a
does
few
it-
seconds behind.
What does it
Actually,
look
like
like?
a minute behind. But
What does it look like?
it's,
Oh. Oh.
do they have the? Okay. Also, the camera is at a weird angle, I think. Okay, yeah, it's
It's
working.
on? Is it?
Yeah, and
What
it's a
does
few
it-
seconds behind. So
What does
it's
it
actually
look
like a
like?
minute behind. But
What does it look like? Oh. Oh.
there we go. They have the. Also, the camera is at a weird angle, I think. Okay, yeah, it's working.
Ah. Is it? I look
And
so
it's a few
stupid.
seconds behind. So
What does
it's
it
actually
look
like a
like?
minute behind. But
What does it look like?
My face is going everywhere.
No, think of the bright side and nobody's gonna watch it. Okay, so we're all good.
I think so.
Okay. This is on, this is also. Okay, there we go. Hello. We're good. Okay, cool.
Actually, let me check audio on this one as well.
Okay.
Let me go inside and then see if I can actually.
Testing, testing. 1, 2. No, even.
Oh, what? 5 days ago?
What?
Oh yeah, because it's unlisted, so we aren't actually doing
Oh,
it.
we haven't updated the
Should we make it public?
publicize the link.
Oh, I see, I
Should
see.
we do it?
We can.
Okay.
Nobody's gonna use it anyway.
All right.
I didn't tell anyone, by the way.
If we run the live stream, is it going to be recorded?
Yeah.
Oh, yeah, then you can.
I mean, it's recording right now, so we may want to.
Yeah.
we
Say something
can.
cautious.
We can do a new one.
It's all right. We can edit it.
So are we going to try and
Make it public?
yeah right now?
Yeah,
Or-
sure, we can.
Okay. Because then, yeah. Okay. I guess
Nobody is going to watch it anyway, right?
I don't know.
Our lab members.
I haven't told
Also send
them.
the link to Jeff.
Oh. That's a good idea.
Richard, are you going to put read the doc on the left side when you're doing the?
I think so. Yeah.
Okay.
Make it public.
Mm-hmm. Okay, and then we send this link to Jeff and our lab member. Where's the link? Oh, this is the link.
Yeah.
So I will send it to.
I can send it also, because everything here is going to be recorded anyways.
Yeah, it's all right. I w-
Actually, we can just switch it to our camera for. There we go.
Okay.
While we're setting up. Oh, Stefan.
How did you know?
He might
already
be
send-
subscribed. He might be.
Wow. What should I say if you? Hey, Stefan, if you are seeing me,
Hola, Stefan.
if you look like to
Can they write a comment?
observe,
Where's comment?
you are more than welcome to observe. And thank you for saving us. So my face is on the live right now, right? Ah,
I think it's a little
you're
bit
more than
behind.
welcome. Okay, no,
It's like a minute
mind.
behind. Yeah, it's okay.
Two watching right now. It's
One of
you
them is me.
and you.
Oh yeah, Stefan said he got a
Hey, Stefan.
notification for the live stream.
So
I don't know how far behind we are, but I think it was like 30 seconds.
okay.
Quite.
Also, let
Yeah.
me share that to our live number. So my face is on the live right now, right? Ah,
I think it's a little
you're
bit
more than
behind.
welcome. Okay, no,
It's like a minute
mind.
behind. Oh.
Two
Wait, was
watching
that
right now. It's
one of
you
them is me.
and
Oh,
you.
oh yeah, Stefan said he got a
Hey,
notification for the live stream.
So
I don't know how far behind we are, but I think it was like 30 seconds.
okay. Also, let
Yeah.
me share that to our live number. So my face is on the live right now, right? Ah,
I think it's a little
you're
bit
more than
behind.
welcome. Okay,
It's
no,
like a minute
mind.
behind. Oh.
Should I put that in? Two
Wait, was
channels
that-
right now. It's
One of
you
them is me.
and
Oh,
you.
oh yeah, Stefan said he got a notification for the live stream.
So
I don't know how far behind we are, but I think it was like 30 seconds.
also let
Yeah.
me share that to our live number. So my face is on the live right now, right? So it means that
I
when
think
we're
it's a little
talking, we cannot move around.
It's like a minute. Oh.
Two
Wait, was
channels
that-
right now. It's
One of
you
them is me.
and
Oh, oh yeah, Stefan said he got a notification for the live stream.
so
I don't know how far behind we are, but I think it was like 30 seconds.
this one. So let me share that.
Oh, I just realized there's probably feedback right now because we didn't mute the live stream.
is on the live right now, right?
Because it's capturing desktop audio too.
Ah, okay. So technically,
Yeah.
oh,
Where is our audio anyway? What is this playing out of? There's no volume. Oh well. Yeah, I'll go ahead and close this anyway.
okay. So we're all good?
I think so.
Will you fix it?
Yeah, I muted the stream.
Okay. It's like we're talking to Stefan right now.
Yeah.
Hey, Stefan. I think we're all good. We can switch back to this one.
Okay.
All right.
I'm wondering actually, should we do a? I'm actually going to set this up as extend, and then the reason for that is that then we can see multiple things, including
Okay.
like the
Sure,
the
sure.
chat, if anybody
Sure.
is actually going to use that or not. But This is probably going to break OBS. Let's see. Where's the... Where's the presenter view? There's no presenter view. Okay, I guess we can't actually have the chat up at the same time. That's
Okay.
okay.
Good.
Yeah, that's fine. Whatever.
Oh, okay, so this is what we're gonna, okay.
So that screen is being shared.
Sure,
And then
sure.
this one is just whatever.
Okay, sure, sure. And when you wanna,
Actually, we probably, no, because when we actually do the demo, we probably
Yeah.
want to be looking at this screen.
yes,
Okay, maybe I should switch it back then. Check that this is...
yeah, but we're not very fucked by that.
Get a piece of paper or something underneath. Yeah, I'm sorry. This is.
No worries, no worries. It's good, you know.
Yeah. So you had like I can't remember the exact number. I can start letting people know to rush in, and depending on how precisely you want to start at, you know,
We
12:30.
are not
Maybe just give it
that
like
strict.
2 or
Yeah,
3
yeah,
more
sure,
minutes or
sure,
something.
Sure,
And
of course.
everything else though is
Yeah,
okay.
well, all
Audio.
all
yeah.
set, all set.
If the mic dies or anything, you just send somebody out here and we'll grab somebody to get a
Okay.
microphone swapped.
Sure.
But yeah,
Other
that's it.
than that, we're all set. Thank you so
I'll be
very
popping
much.
in and out, but I'll
Okay.
probably just be out there a little bit just to
Sure.
make sure that.
Sure, sure, absolutely. Thank you.
But I definitely will come back for your tutorial later.
Thank you.
I'm gonna close this for a second.
Okay, okay, thank you. Thank you so very much for coming, folks, and we probably give it another 2 minutes before we get started. Thank you. And meanwhile, you may want to start to look at that document, because that one has everything you need today. We're gonna need a lot of hands-on coding, or it will be more convenient if you can open the terminal and run through all the examples with us. But it's fine if you don't want to. You can just watch us do that. Yeah, you can actually go up and see.
Maybe just in case anybody has questions, this is the Wi-Fi
Wi-Fi.
DTOA 2024. It's the Doubletree Orlando Airport.
Oh,
If it helps you with the acronym.
okay.
And then this is to get the proceedings to download the zip
Okay.
file, and then this is just the general program. But if they need Wi-Fi access,
Okay.
I'm gonna have Jeff print a bunch more, and he can
Okay.
hand them out. But
Okay.
that way you have a copy. I really can't believe they didn't get that. That's really annoying.
Oh, it was fixed 5 minutes ago.
Of course, this is just the cheapest.
No worries, not a problem, not a problem. It's all right.
Take this.
Oh, it's fine, it's fine. We're not too
But
bugged by that.
you're so accommodating.
Yeah, no worries. Don't worry about it.
Oh, maybe I'll ask them to. I'm just trying to think if I could tape like a stick or something behind it, to, like make it more rigid, right? Like you think that would make it work?
I think we could just leave it as it is.
Um,
It doesn't bug us too much.
Well, I don't know, you can. So for you guys sitting, you may want to be more over here, just because the screen. We're trying to get the hotel staff to fix the screen, but it's a little wonky. So you may want to be on that side, just to make it easier.
Follow-up question. So is there gonna be like interactive component we should bring our laptops?
Yes. I'll let
Is there gonna be
Kelly.
like an interactive that we should
Yes.
bring our laptops
Yes,
here
yes,
for?
yes,
Okay, so
yes.
maybe we should go back.
I think we can get started in 1 minute. How does that sound? And by the way, this is the Wi-Fi information. If you haven't accessed, this is Wi-Fi information. Let me know if you need to take a closer look. Anyone need it? Okay. All right, folks, I think we can get started. We're gonna get started. Okay, thank you so very much for coming today on the first afternoon of this FCCM conference. It's my greatest pleasure to be here to do this tutorial. So, my name is Kelly Hao. I'm going to introduce myself later, but today this is about our tutorial, understanding your FPG design better from rapid simulation to onboard profiling. We have 3 presenters. Myself, I'm just going to do the brief introduction for like 5 minutes, and then we have 2 presenters, Rishal Sakar and Jiho Kim. They will do 2 tutorials, one for Lightning Sim, and then the other for onboard profiling, RealProbe. So a big, huge thanks to Dr. Jeffrey Young, the director of Crunch. And this session will not be possible without his effort and tremendous support. So a big thank you to Dr. Jeff and Georgia Tech Crunch Center. So this is a little bit about myself. My name is Kelly again. I'm assistant professor at Georgia Tech. This is my 3rd year, and I got my PhD in Japan. I just want to say I used to be a fun person. I hope I'm still a fun person. And I want to talk more about fun fact other than research. So reach out to me later. We can talk all about fun facts. And this is about my lab. I'm super, super proud of my lab. My lab is called Software Hardware Co-Design for Intelligence and Efficiency, and it's called Shark Lab. These are my cute students, and this is our lab shirt. As you see, here's a big logo, and that's our logo there. So all the tremendously nice work are done by the students. I take 0 credit. Okay, so what are we talking about today? I believe that anyone sitting in this room are enthusiasts of FPGA boards. Are we? We are, right? Otherwise, we're not gonna be here. Now, who are enthusiasts of high-level synthesis? Who likes high-level synthesis? Or some of, maybe. I don't see you guys are not, I don't see you are very enthusiastic or happy about HLS. Maybe it's because you see a lot of problems about it, right? That's why we are here to help. But we are enthusiastic of HLS. And Risha will give you more detailed reason why we like it. But in my opinion, the ideal world of HLS and FPGA are just fantastic. So assume that you have a piece of C++ code going through high-level synthesis. You just immediately get this massive Verilog code you don't have to write on your own. And based on this Verilog code, you can just do some C RTL code simulation, or if you're more familiar with RTL simulation, you just run it, check your functionality, check your design performance, and bam, you just deploy that to the FPGA, right? That's the ideal world. Everyone is so happy about it. Now you don't have to write Verilog. You have a perfect FPGA, you have a perfect FPGA design. Everyone is happy, everything seems to be working fantastic until something goes wrong. A lot of things can go wrong, right? I see a lot of you are smiling and nodding. A lot of things can go wrong. Until you're happy, until your FPGA design goes crazy, and then you go crazy, right? So what can go crazy? A lot of things can happen. So on the left side, during this translation from high-level synthesis, from C code to Verilog, a lot of bugs can happen. You have to do a lot of manual effort. That part, we're not touching that today. I just assume we're all HLS experts. We're not doing that today, but if you are interested, I'm happy to do another tutorial maybe next time to talk about the left part of this design flow. But today, we're only focusing on the right part of the design flow. Here, from CRTL code simulation to FPGA deployment. What can go wrong there and how can we fix it? So the first problem, I'm pretty sure you know that RTL simulation is like incredibly slow, right? It can take hours, even days. It's just insanely annoying. You cannot just sit there and wait for your design to be simulated for a couple of hours or a couple of days. Your boss will fire you unless you are the boss sitting in the room. But my boss will not allow that. I mean, I'm the boss. So things can go really, really slow. We don't like CoSim. It's too annoying to know our design performance. The next thing can go wrong is once your design is deployed on the FPGA board, you don't know what's happening, right? It's like a black box to you. There's no way that you can open the chip and look at the signals inside. If your design doesn't work, it doesn't work. If your design slows down, it slows down. You don't know what's happening. So now things can go crazy, and you're really like scratching your head, what the heck is going on? Why it is taking so long? Why my design is so slow? So, can the HLS and FPGA world be better? Just save us. We are poor engineers. We're already miserable enough. Please help us be better. Can this world be better? Now, in order to answer this question, we have two major concerns. Question one, like we said, do I really need to wait for hours and days to run CoSim? CoSim gives you fairly accurate HLS design performance in terms of clock cycle counts, and which is something you really need. CoSim is good, right? CoSim gives you a fairly accurate cycle count. Wow, but do I really need to wait for hours or days? And the second question, what is happening inside my FPGA design? I generate a bit stream, I deploy that to FPGA, and I can only run it and observe the end-to-end latency that I measured on the FPGA board, right? What's happening inside? I don't know. I don't know what's happening. Why is my design on the FPGA performance is twice slower or even 3 times slower than the CoSim? What is happening? Can you know that right now? Well, I mean, if you're really an FPGA nerd, you can go very deep and probe all those signals, but it's just too annoying. There's no easy way that you can know it better. So, these are really two big questions that we want to address to make this HLS plus FPGA world a better place. That we want to run the design, we want to run the simulation faster, and we want to know exactly what's happening inside your FPGA design. And I really encourage you to use high-level synthesis, to use HLS, in every opportunity you can, because that can save you a lot of time. With HLS and with our tools, I'm pretty sure designing FPGA is no longer a pain. Okay, so yes, I think we can. We can make it a better world unless, as long as we address these two questions. So to address the first question, do we really need to wait that long? No, absolutely not. If you use HLS and if you use HLS plus our tool called Lightning Sim, I promise you that you can almost 99% of the time get rid of CoSim and get your design performance back in a few seconds or at least a minute. And to the second question, we are providing a real probe tool that can help you to open the black box of your FPGA and see what's really going inside. Why your design is slowing down, which module, which subfunction, which loop is slowing down. And it's, again, a very easy to use tool, and it will help you make this FPGA at HLS world a much better place. So this is what we're going to cover today, and we are going to have two presenters. The first presenter, Mr. Rishabh Sarkar, he is going to introduce Lightning Sim. So this will be the first half of this tutorial, probably gonna take roughly an hour. And then the second half of the tutorial is Ms. Jiho Kim, and she will introduce our tool, Real Probe. It's also going to take roughly an hour. So this tutorial will, they will introduce what the tool is, they will introduce what the tool can do, the big idea of the tool, and then they will walk you through a few coding examples that you are highly encouraged to try out those examples along with them, and they already set up the environment for you. It's highly encouraged, but it's fine. If you don't want to do, you can just sit here and watch those examples, and feel free to try out later, because all the materials are already online. Okay, so that summarizes the opening, and I will going to pause for 5 seconds if there's any questions. If no, I will hand over to Mr. Rishabh and Ms. Jiho. Are we all good? Okay, awesome. Thank you. So now let's welcome our first presenter, Rishabh, to introduce the Lightning Sim.
Thank you so much for the introduction. Hello, everyone. I'm Rishabh. I'm so excited to present the first half of this tutorial on Lightning Sim. This is the, if you read the title of our tutorial, Understanding Your FPGA Design Better from Rapid Simulation to Onboard Profiling, this is the rapid simulation part. So I'm so excited to present this work to you. So here's the tentative schedule for this part of the talk. We're already a little bit behind just because we started a little late, but hopefully we can catch up. But I'm going to spend roughly 10 minutes on just introducing what the tool is and how it works. Then we're going to spend about 40 minutes on hands-on experiments, and then if we have time, we'll take a 10-minute break and do some troubleshooting as needed. I'll come around and help people with anything that needs to be helped. So the outline for this talk, I'm going to start with some background on what high-level synthesis is and how you simulate HLS designs right now. I'm going to introduce the key insights and ideas behind our tool, Lightning Sim, and then I'm going to introduce the tool itself, how it works, and some of the results that we've collected using the tool. And then we'll move on to the hands-on experiment section. So starting with the background, as Callie mentioned, high-level synthesis is a great tool. You can take something like C or C++ code and run it through this tool, and it will spit out Verilog or VHDL at the other end. Great. You never need to worry about writing Verilog or VHDL ever again, right? So this is great because it's easy to learn. You might only need like 1 month to learn it, especially if you already know C or C++. It's not that much of a jump. And it can be very highly productive. Complex designs that might take like thousands of lines of Verilog, you might be able to write much faster with high-level synthesis. What might take 6 months to do in Verilog, you can do in 1 month with HLS. What might take 1 month to do in Verilog, you might be able to do in 1 day with HLS. And because it's just C or C++ code, you know what it's doing. You can debug it just as regular C or C++ code. But you may not be convinced, right? So you may have some questions about this Verilog that's being produced here, right? Like, how fast is it? If I write the Verilog myself, I know exactly how many clock cycles everything is going to take. If I just hand it to this black box HLS synthesis tool, I have no idea, right? It could be taking 1 million cycles to do an add or something. How do I know what the performance is? And additionally, how do I even know that what I get out the other end is correct? How do I know that this is doing what I actually want it to do, right? So that brings us to the different ways that you can simulate HLS designs. The easiest way is what we call C simulation. This is basically where you just take your HLS C or C++ code along with C or C++ test bench, and you just compile it and run it like a regular C program. Now, what this will do is, of course, it just tests that the C or C++ code that you've written is correct according to your test bench. So it gives you a functionality check that if your input is correct, then your output is likely to be correct too. But then, if you want to know the performance of your design, after you run this HLS synthesis process, you also get a report at the other end. And the report tells you, along with the Verilog code, it tells you how many cycles the HLS synthesis tool expects that your code is going to take. It might say that, that this function is going to take this many cycles, this function is going to take this many cycles. It adds them up and gives you the total latency of your design. But if you need an even more in-depth check, then you can get your cycle accurate performance and like low-level hardware functionality check using what's called CRTL cosim. This is called co-simulation because what it is it takes the RTL, the Verilog code that's generated by HLS, and it takes your C test bench, or C or C++ test bench, and it basically combines them and runs the RTL code as if it's a part of this flow. So it gets the actual, it takes the actual RTL code out the other end and basically collects feeds in the inputs, gets the outputs, and feeds them back to your C test bench. That's why they call it co-simulation. And this is the most accurate simulation method here because it can actually, it's actually simulating the hardware level RTL. So we have these three methods of simulating HLS designs. And so if we want to check correctness, we have two options. We can do C simulation. The problem with C simulation is that it's limited in scope and not necessarily reliable, right? Because just because your initial C code works doesn't necessarily mean that the final RTL code is going to work. There are certain things that, that can't be simulated at the C level. So for example, if you use what are called HLS streams, you might encounter deadlocks, and deadlocks actually can't be detected at the C simulation level. On the other hand, if you do C RTL co-simulation, that's much more accurate. It will give you the actual, it will tell you, hey, there's a deadlock here, or hey, your design ran all the way through. And you can actually check the output with the test bench, and you know that it's right because it's using the actual RTL from your HLS synthesis. Now, if you want to check performance, as I mentioned, you have the HLS synthesis report. But the problem with the report is that the estimates in terms of cycle counts and latency are not necessarily reliable. They're roughly estimated because it's basically based only on static analysis. It's only the estimates in the report are only based on what HLS can figure out about your code without actually running the code, right? It can only tell you, it can only estimate this loop I think is going to run this many iterations. These functions I think are going to happen in this way. So it's not necessarily reliable. And so C RTL co-simulation, again, solves this problem. It's much more accurate because it has the dynamic behavior of what is actually happening based on a certain test bench, a certain workload. It can tell you this loop ran exactly this many times. This function took exactly this long. Now, the problem here is that C RTL co-simulation, as Callie mentioned, is much slower than C simulation, right? So we have kind of a spectrum here where C simulation is the fastest thing you can do. You just compile the C code and run it. It might take maybe seconds. Whereas HLS synthesis, the report might come after a few minutes, and C RTL co-simulation could take hours or days. But on the other hand, if you want the actual accurate performance and functionality benefits, then you actually need C RTL co-simulation, especially when you're dealing with things like, I want to check if my design has deadlocks. The only way to do that is with C RTL co-simulation. Neither C simulation nor HLS synthesis can tell you in advance whether you have a deadlock. So what if we had a tool that can combine the speed of C simulation and the accuracy of C RTL co-simulation? Well, now we do. It's called Lightning Sim. And it's not a trade-off between these two ends of the spectrum, but it actually has advantages of both sides. So as we mentioned, C simulation is the fastest simulation option, but it can't do any cycle level simulation, and it does only high level functionality verification. Meanwhile, C RTL co-simulation is the slowest simulation option, but it does cycle level simulation and can verify at the RTL level. With Lightning Sim, you actually get a pretty fast simulation, almost as fast as C simulation alone, but it also gives you cycle level performance And it can also do a deeper functionality check by simulating at what's called the LLVM level based on the intermediate representation that is generated during the HLS synthesis process. So it actually gives you more confidence in your design if it works under Lightning Sim. Additionally, Lightning Sim can introduce several new features that aren't possible with previous versions of previous simulation solutions, such as what we call incremental stall analysis, where in certain cases you can just tweak certain parts of your design and it doesn't have to do a full simulation again. It can just give you an updated simulation in milliseconds. And it can also, if you use first in, first out FIFO streams in your design, it can actually suggest what the fastest depths will be for you just from one iteration of the simulation, which neither C simulation nor C RTL co-simulation can do. So the key idea, let's go on to how the key ideas and insights behind Lightning Sim. So the way this works, the way that we came up with Lightning Sim is by examining the HLS synthesis process itself and looking at these individual steps. So the first step in HLS synthesis is front-end compilation, where we take the initial C or C++ code and it will actually generate what's called LLVM, intermediate representation from the source code. This intermediate representation is basically like a lower level, think like a high level assembly language, if you will. It has low level operations, and if you're familiar with like basic blocks and control flow graphs, it's basically lowering the C or C++ code into something much easier to work with. Then, with each of these operations defined in the LLVM, the HLS tool will do what's called scheduling and binding. And for our purposes, the important part is scheduling, where it will actually determine how functions and operations are scheduled. So for example, if you have two functions A and B that can be executed simultaneously, this is when HLS figures that out and decides to put them in parallel. And similarly, if you have a loop that's pipelined, this is when HLS figures out how that loop should be pipelined, what initiation interval, what pipeline depth we need for that loop. And the result of this scheduling is you get these basically this finite state machine here with these states, and each operation is mapped to one or more of these states. And so what's interesting about this is that usually, barring stalls, which we'll get to, this actually is usually one clock cycle per state. So we could actually maybe use this for a faster simulation, because we don't actually need to know anything. We only need the scheduling information to figure out how many clock cycles something is going to take. So we might just be able to use the scheduling information alone. And the other insight we have is that if we can just use the scheduling information, then we don't actually need the RTL code either. We don't need the Verilog or VHDL. We can actually start or even finish simulation before the RTL generation step is complete. Sure. We can take questions now. Yeah. Yes, yes. So right now, everything we're covering is based on Vitis HLS. I do believe that other HLS tools do work similarly in terms of a lot of them use LLVM and do the scheduling process. I'm not too certain of the specifics there, but so the question is about code coverage and getting the doing simulation of like getting more coverage in your simulation. And I think this is not something that we've considered yet with Lightning Sim, I think, but it's something that definitely could be a future direction for this, especially because we can operate at the LLVM level and say like these LLVM instructions are the ones that are being executed. And so it's definitely a viable extension for Lightning Sim. So I'd be interested to see. Yeah. Right, we're not changing the scheduling. What we're doing is we're actually taking the LLVM and just like mapping it to the schedule and. So all the scheduling that was set by the code and the pragmas. Right, right. The scheduling is just whatever Vitis HLS produces. So that's anything from the pragmas or that it decides to do automatically. So. Okay, so easily readable. You're saying the scheduling information? Yeah. So. Easily readable, I think, is a bit of a stretch, but with some engineering effort, I think it is possible to basically disassemble the LLVM and figure out how that maps to the scheduling finite state machine. Right, exactly, yeah. So the HDL is much lower level and a lot more difficult to debug and operate with than the LLVM. So that is one major advantage of using the LLVM for this sort of thing. So the idea is that we start with what we call these static stages in HOS, where these are the scheduling results. So basically, in green here, I have that schedule that I just showed on the last slide. And the idea is that each operation is mapped to one or more states, which I call static stages, that reflect the possibility of simultaneous or sequential executions of modules and operations. So for example, in this example here, function A and function B can execute together, so they're mapped to the same state. And the loop body and the loop condition can execute together, so that when the loop condition is mapped to state 3, the loop body can also execute as part of the state 3 in this finite state machine. And then of course, we actually have to have the finite state machine itself, where the loop condition might cause the loop body to execute again. So you might need this finite state machine here, where state 3 goes back to state 2 based on the loop condition. Then what we do in Lightning Sim is we take this concept of static stages and basically unroll it into what we call dynamic stages, which are the actual executions of these states under a given test bench or workload. So for example, let's say that in this example, the loop would execute 4 times under a given test bench. Then what we do is we unroll the schedule based on this test bench execution, and we get what we call these 9 dynamic stages. Then, to get the actual cycle count from these dynamic stages, we determine and insert the stalls that are necessary to make everything line up. So for example, if function A takes 3 cycles to execute instead of 1, then what's going to happen in the hardware is that it will stall this module until function A is complete. So we insert 2 cycles for the stalls. And similarly, for function B, let's say it takes 4 cycles to complete, then we might need to insert 3 cycles of stalls to make to determine the actual cycle count of this function being represented here. So these stalls, of course, are what are calculated during C RTL co-simulation, but the key idea behind Lightning Sim is that we might not actually need the RTL for this. So what we do is we obtain the static stages from HLS synthesis, or the scheduling process. We figure out the dynamic stages based on a test bench execution trace, where we actually run the test bench and log basically every instruction that's executed, so that we can then figure out how many times each loop ran, or what sort of basic blocks were executed, and we can do this sort of unrolling. And then finally, we resolve stalls through basically a custom algorithm to figure out what the final cycle count is, where we basically model what would happen in the actual hardware. So now we can introduce how Lightning Sim works. So we start, as I mentioned, with the LLVM IR from HLS synthesis, and we compile and run that under a test bench, that test bench being the user-provided test bench that you might use with C simulation or C RTL co-simulation. It's the same test bench. We just compile and run it. And then we collect that execution trace that I just mentioned, that we can then analyze to calculate the design performance, get the dynamic stages, and then finally the cycle count. And thanks to our decoupled approach here, where we have like this separate trace generation step and this trace analysis step, we can actually do something even more interesting, which is that if you use, as I mentioned, the HLS stream construct, where you have like these first in, first out streams, and you have to set a certain depth of the FIFO buffer, then if you just change the depth, we can actually just incrementally resimulate that in milliseconds without having to actually do a full simulation again. We just do a recalculation of the stalls, and we can figure out how long that will take, or even if it deadlocks or not. So we evaluate Lightning Sim on 33 benchmarks using AMD Xilinx Vitis HLS 2021.1 as our baseline, and we get 99.9% cycle counts on 99.9% accurate cycle counts on average relative to co-simulation. And actually, in 26 of the 33 benchmark cases that we tested, we actually achieved perfect cycle accuracy with CoSim. And we do this in up to 2 orders of magnitude speed up over CoSim. Our results are also reproducible. We have the benchmark scripts on our GitHub repository. So now, with that out of the way, I think we can move on to the hands-on experiments. So this is the fun part. So everybody, if you don't have your laptops out already, I would recommend that you grab your laptop and go to this URL, lightningsim-doc.readthedocs.io. And then from there, go to the FCCM 2024 tutorial page. So I'm actually going to do that now, and I'll do the tutorial basically with you guys so that we can see how this works. So this is the Lightning Sim documentation page. So just click on either, you can click on the FCCM 2024 tutorial link in the sidebar here, or you can click on this our hands-on tutorial link right here under Getting Started. So just some quick information about the tutorial, which you already know, that like which session this is, and information about the schedule. So if we move on to the Getting Started page right here, we're going to see we have instructions both for you all, the in-person attendees here at FCCM 2024, and we also have some remote instructions. If you want to follow this tutorial later and explore on your own time, please feel free to do so. I have instructions on how to set up your environment and run these examples on your own. So let's go ahead and click log into the system here for the which takes you to this login to Crunch resources page. Once again, I want to give a huge shout out to Dr. Jeff Young from Crunch for all his support in getting this set up. So you can see here there's a link to access the Crunch resources. Visit this URL right here, synestia-ood.cc.gatech.edu. So I'm going to go ahead and open that in a new tab. And you'll see that you'll be prompted to log in. Oh, if I wasn't already logged in, you'd be prompted to log in with your Georgia Tech credentials. We have a link to a spreadsheet here, and this spreadsheet will have a list of accounts and the password for these guest accounts. So go ahead and put your name next to one of the accounts to indicate that that's the one you're going to use for this tutorial, and use that username and the password at the top of the spreadsheet to log in to the Georgia Tech website. And once you do, you should get this interface that says Open on Demand.
Please let me know if you have any questions, any help.
So I'm already logged in here, but once you log in, you'll see this interface. Actually, it looks a little bit different when I have the window full width. You can see there's a few tabs here. The important ones for our purposes for now is this Synth and EMU tab for synthesis and emulation.
Hold on a second.
Sure.
I think someone has been trying to log in.
Okay. All right, so once you've logged in, as I mentioned, you'll see this page that says Open on Demand, hopefully. And then you'll go to, so there's an interface for both the pink boards. That's actually something we'll use later in the tutorial when we get to the Real Probe section presented by Jiho Kim. And for now, what we're going to do is we're going to go to the Synth and EMU tab, and we're going to click on Synestia Desktop. As indicated here in the screenshot, you can just click on this, this entry here that says Synestia Desktop. When you click on that, you'll be presented with this page that asks the parameters that you want to use to launch this VM. The account, leave this text box blank, just and leave it empty. And then for number of hours, increase this to 3. And then for number of nodes, you can leave that at 1. So once you've entered these, go ahead and hit launch. And we're going to wait a few seconds, and we should get a desktop running. All right. Everybody good so far? All right. So I'm going to go ahead and hit Launch Synestia Desktop. And actually, I'm going to decrease the compression and increase the image quality just for... All right. So now you should see this desktop. So I think, yeah, we're now good to go ahead and try out Lightning Sim. So And I'm also going to put this side by side here. So Lightning Sim, the way that I have packaged and distributed Lightning Sim is as a Conda package. So if you're familiar with the Anaconda or Mini Conda software, this will seem very familiar to you. So this is typically used for Python projects, but it's great for distributing binaries as well. So I use it to distribute some LLVM components that we need and things like that. And the great thing about it is that it doesn't require root. So if you have like an HPC server or something like that, that you want to run this on, you actually don't need root access. You can just install you can install Conda, which doesn't require root either, and you can just use this that way. So there's just one single command that you need to run in order to actually install this. So I've already set up Conda for on all the guest accounts. So you should be able to see when you run Conda, you get that. So go ahead and run this command right here, this Conda create. The parameters themselves are a little bit long, but basically what it's doing is it's pulling the Lightning Sim package from our GitHub repository and some dependencies from Conda Forge, and it's putting them into a Conda environment named Lightning Sim. So when you run this command, hopefully it shouldn't take too long. I have pre-cached all the packages you should need, hopefully, so it should run hopefully pretty quick. But let's see. All right. Almost there. Any questions so far on the installation process or anything in general? Yeah. The what? Oh, so go ahead and copy that from this page here on the install Lightning Sim page. You should just be able to copy paste directly into the virtual machine. Basically, it's creating a Conda environment with the name Lightning Sim and -y is just to confirm. It creates with the name Lightning Sim and uses our GitHub repository as a source as well as Conda Forge for other dependencies and installs the Lightning Sim package. So that's where all those arguments come from. But you can just copy paste it directly in. So. Seems to be taking a minute, but hopefully done soon. Sure.
So you said 99.1 or 99.9% coverage. I was curious about where this fails.
So right now, the point of inaccuracy. Oh, sure. So the question is about the accuracy number that I presented, the 99.9% accurate on average, and the question is where does Lightning Sim fail to achieve 100% accuracy? And the answer is that it's basically the model that we are using for the external memory interface, the AXI interface, is not part of, it's not in like any of the scheduling or LLVM information. It's just, it shows up as like call AXI read. So basically what we do is we have a model that, that simulates as close as possible what CoSim is trying to do when it does these AXI reads and writes, but it's not perfect. So it doesn't achieve 100% accuracy when those features are used.
I have another question.
Sure.
Mine seems to
Okay, yeah.
Anyway, we've been using a tool, I'm just wondering if you're familiar with it, how it like compares to Verilator.
Yeah.
Verilator, which is, I mean, it's a similar, I think it's a similar concept in that it takes RTL as RTL and then it basically says, hey, what's RTL, what does it see instead?
Right.
And it runs it on that basis. And I don't know how cycle accurate it is comparatively speaking. Probably, I think it's pretty high. Yeah, I'm not sure. So I'm just curious if you have, you're familiar with it, like how the comparison goes there.
So-
Speed, accuracy.
I am familiar. Basically, it is. Oh, right. So the question is about the tool called Verilator, which is another Verilog simulator that basically takes the Verilog code and basically generates equivalent C code and compiles that and runs it to do the simulation. And so I am familiar with it, but it is basically it's an RTL simulation of its own. So we don't actually directly compare with it. It is part of the idea in Lightning Sim is that we are trying to move the simulation as early as possible. So we don't, we're trying not to use the RTL itself because we believe that using the LLVM, doing simulation at the LLVM level can lead to greater speedups, especially when you have large designs. As I don't think we'll be able to show in the tutorial itself because of time constraints, but when you have large designs, RTL generation can take a long time. So for example, we had, in our experience, there was one design that takes like 5 minutes for the LLVM compilation, 5 minutes for scheduling, and then another 5 minutes for RTL generation. And in the time it takes to do this 5 minutes for RTL generation, Lightning Sim is already done. So it actually, so by sort of using the LLVM level, we can achieve greater speedups for larger designs. But we haven't done like a direct comparison to see on small designs, especially how Verilator would compare. All right, but yeah, thank you for the questions. So this installation is done, so I'm going to go ahead and run this conda activate command. And what this is going to do is it's going to set up the this shell to have access to the Lightning Sim package and the Lightning Sim commands. So you can see that's indicated here by this parenthesized Lightning Sim right here. And so now this environment is active, so we should have access to this to the CLI command named Lightning Sim. So if I just run lightning sim -- help, we should see some usage information spit out. Shortly, hopefully. There we go. Yeah, so this is just the information on how to run it. And then the next thing that we want to do is Lightning Sim is actually expecting the environment to already be set up for Vitis HLS. So we're going to be using Vitis HLS 2021.1. The reason that we're using this specific version is that although Lightning Sim will run with newer versions, the AXI interface that I talked about has actually changed even more. So the model that we use has become way less accurate for those, but we are working on implementing the new AXI model for the latest versions of Vitis HLS. But for now, for our purposes, we are just going to try out Lightning Sim with 2021.1. So I've created a sim link in our home directory for a few versions of the Vitis HLS software. So if you just run this source settings 2021.1.sh, you should now, it won't spit out anything, but it's basically set up the environment for Vitis HLS. When you do this on your own machine, it's actually going to be, of course, whatever path that you actually installed Vitis HLS at, /2021.1/settings64.sh. But for your convenience for this tutorial, I have just sim-linked it so that you don't have to type out that full thing. All right, so now we can go on to the examples themselves. So I'm going to start with like an end-to-end flow that basically is intended to demonstrate how you might use this in like a day-to-day, like if you're developing an HLS design, how you might use Lightning Sim as part of that development workflow. So the example is derived from the Parallel Programming for FPGAs book, which, by the way, is a great book that introduces high-level synthesis and gives you a bunch of examples. It's a great resource for anyone looking to get started with HLS. So anyway, we can go ahead and launch Vitis HLS 2021.1 from this desktop shortcut. So I'm going to double-click that. And wait for it to launch. Oh boy. Hopefully it still works. Okay, so we have Vitus HLS open, and you can see this open project link. So I've already downloaded the examples for you, so go ahead and go into this examples folder, click on example 1, and click open. Change the sizing a little bit. All right, and there we go. The project is now open. So we already have the source files and test bench files that we need here. This is we have like a matrix multiplication example along with a test bench to test it. So let's go ahead and before we actually synthesize this design, I'm going to launch Lightning Sim just to show how it works side by side with Vitus HLS. So if I just, in the same terminal where we have this Lightning Sim environment active, type in Lightning Sim, and then put in this path, examples, example 1, solution 1, with no hyphen between the solution and 1, but yeah. So one thing to note is that whenever you use Lightning Sim, you're supposed to pass a path to the solution itself, not the project. So the project is located at example 1, and then we have a solution inside named solution 1. So pass the path to solution 1. So it's going to print a URL. So if you control click this URL, it will open the default browser, which I believe is Firefox in this virtual machine. Perfect. All right, and you can see it's sitting here waiting for the next C synthesis run by default. So I'm going to go back to Vitus HLS, and actually I'm going to maximize the window for this, hopefully. And I'm going to show you what happens when I run synthesis. So I'm going to drag this over here, and I'm going to click this play button. And just hit OK to confirm the default settings. All right, so synthesis is running right now, as you can see. All right, and Lightning Sim has picked that up, and it's running the simulation. All right, perfect. So now, oh, and also I should have, so Lightning Sim started simulation a few seconds into the synthesis process. We also can see how long co-simulation is going to take. So let me go ahead and run co-simulation. It shouldn't take too long for this design. It's intentionally very small. It's just a simple matrix multiplication. So, but yeah. So I mean, Lightning Sim obviously already completed because I didn't start COSIM yet, but you'll actually see even as COSIM is running, you'll see that Lightning Sim actually was able to complete significantly faster. So in the meantime, I'm going to go ahead and navigate to this output tab. So the output here, if it actually works, yes. So the output here is basically what the C test bench has printed. So it's lagging a little bit, but this is just, oh boy. Okay, yeah, so you can see at the bottom here, I have the exit code 0, and you can see in the log it says pass, the output matches with the golden output. So we know that everything seems to be working, that the simulated test bench is passing. And once COSIM completes, we'll see that actually it gets the same result. So I'm gonna go ahead and navigate to the overview tab while COSIM is still running. And you can see the latency here. It says 32,771 clock cycles. And when COSIM is actually complete, we'll see that that is actually the same between Lightning Sim and co-simulation. Hopefully it shouldn't take too much longer. So the RTL simulation actually just started. That was all just setting up the RTL simulation.
I guess while we're waiting for that, okay, one more.
Yeah.
I noticed that the synthesis latency estimate looked quite close to the lightning sim latency estimate. Are those things that you expect? Like,
So for this design, so actually, yes. So the question is that for this design, the synthesis latency estimate, which if I can find it here, if I can actually scroll this, that'd be nice. Right, so right now the synthesis, this is COSM. The synthesis estimate says 32,773 cycles, and Lightning Sim right now is reporting 32,771 cycles. So this is actually a pretty ideal case because a lot of the time, so in this case, it's basically just simple loops and things like that. So there's not much for that Vitis HLS can't statically predict. So it actually achieves a pretty close estimate to both what COSIM reports here is 32,771 and what Lightning Sim is reporting, which again is 32,771. So yes, that is expected for this design, but in the next ones we'll see where that fails. So yeah, so our kernel is apparently taking 32,771 cycles to complete during the simulation. So let's see if we can extract some more performance from this design pretty quickly. So I'm going to go ahead and open the source file here, this matrix multiplication.cpp. And we can see that right now there's a triple nested loop. And the innermost loop here is pipelined. This product loop is pipelined. But maybe we can actually get away with moving this pipeline statement up to the loop above it, which will cause the product loop to be unrolled and have this nested row call loop execute with an initiation interval of 1. So let's see if we can actually get some more performance that way by moving this pragma HLS pipeline II equals 1 line from line 15 to line 12. Then save the file. And what we're going to do first is we're going to prepare Lightning Sim for another simulation run by going back to the status tab here and hitting rebuild. And again, it's going to start waiting. So now I'm going to run C synthesis again. And we'll see. Hopefully, if it doesn't take too long. Where's the progress? Oh, it's right here. Let me actually try reconnecting real quick. Okay, yeah, so synthesis actually completed. It was just lagging on here. But you can see that Lightning Sim is also complete. So, and we can look at the overview, and we see that the number of cycles now is only 1,027, so the performance improved a lot. So basically the idea is that if you wanted to use this in development, you might just have this cycle of like, you edit your file, you resynthesize, and you have Lightning Sim also running, and you just you can just keep updating your estimates that way. So now that we're done with this, we can go ahead and close this Vitis project. And I'm going to go ahead and also kill the Lightning Sim process. You just hit, go back to the terminal where you launched it and hit Control-C, and it should exit Lightning Sim. And you can close this browser tab as well. All right, and so that's the first example. So in this example, you saw how to run it on run Lightning Sim on a Vitis HLS project within a development workflow. And as one of our audience members pointed out, the simulation wasn't actually necessary for this example. The HLS report itself already provided a very close estimate of the cycle count. So in the next examples, we'll see that this isn't always the case. So Lightning Sim can help a lot more for these next examples. So example 2, maybe I should probably skip a couple of these examples just because of time constraints. But I'll go on to actually, we can go on to the pre-synthesized example. So go ahead and click next up till example 4, which is labeled a more complex design. So the idea is that Lightning Sim is actually really helpful when it comes to larger, more complex designs that take minutes or hours to synthesize and simulate. So this is actually one of our previous projects called FlowGNN, and it was basically the inspiration for this tool in the first place. So go ahead and click on Open Project, go to Examples, and go to Example 4. And this example, I've already pre-synthesized and simulated, or no, I didn't do the simulation, but the example is already pre-synthesized for you. So we're going to wait for that to open. And in the meantime, we can also go ahead and launch Lightning Sim on this example too. So I'm going to go ahead and run this command. So this is actually a very similar command, but I've added this flag skip wait for synthesis, which, as the name implies, Lightning Sim usually starts up with that wait for synthesis thing because it expects that you're using it in a development workflow. But if you're just trying to run it on a pre-synthesized design, you can add this flag and it will skip that step. So let me go ahead and do examples, example 4, solution 1. Again, remember, you want the solution path. And you can also achieve the same effect for the skip wait for synthesis by, there's a link in the UI that says skip when it's waiting. So if you click on that, it will do the same thing. But for now, we're going to see this. Did this even open? It's still thinking about it, it looks like. All right. And so Lightning Sim is kicked off. Hopefully the project actually opens soon. Otherwise, I'll just go to the command line report. Yeah, okay. Right. So unfortunately, I don't have the code simulation report here for you all to compare, but this is the synthesis report of the pre-synthesized design. And you can see here, it's estimating that the latency will be 216,001 cycle. So if we wait for Lightning Sim to complete, this actually will probably take about 1 more minute or so. The runtime can vary a lot depending on the system that you're running it on. So if you're running it on like an actual HPC cluster, this might take like, or actual HPC server might take less time, but I think the compression might also have something to do with it. Yeah, let me try this real quick. All right, so now Lightning Sim is done, and you can actually see that the latency that it reports is 260,337 cycles. And so that's actually a lot different from what we got in the synthesis report. And unfortunately, I don't have the co-simulation report here for you, but the co-simulation estimate is actually about the same. It's 2,359 cycles from co-simulation. So Lightning Sim is pretty close here. So you've probably pretty clearly noticed that the estimate that it gives here, 216,000, is a lot different from the simulated result of 260,000. And so you might be wondering why these numbers are so far apart. There's several factors. So one is that the behavior of this design, which is, it's a graph neural network accelerator, so it operates on graphs. It's very dynamic and data dependent. So a lot of the loops in the source code for this design have this loop trip count directive that gives HLS an estimate of how many iterations that loop is going to take. But if you put that estimate, there's HLS, first of all, has no way to verify that. And second, if that loop varies at runtime with the number of iterations varies at runtime, then it's not very useful. So it can result in pretty inaccurate estimates. Additionally, this design makes use of HLS data flow, and the statically generated estimate for HLS data flow is pretty bad because it estimates the overall data flow latency as the longest estimated latency of any data flow subprocess. So you can see here's the data flow process, and you can see there's this one process that takes 1,131 cycles estimated, and this process takes 708 cycles estimated. And so it just estimates the overall latency as 1,131 cycles, which is basically a best case estimate of these already bad estimates. So it's not very good. And then additionally, as I mentioned, this design uses AXI interfaces for top level memory access. And so this causes additional delays that static analysis can't take into account. So if you have any of these characteristics, the synthesis report will be, can be significantly less accurate than co-simulation, and this is where Lightning Sim can help. And so, yeah, unfortunately I don't have the co-simulation report, but another thing is that co-simulation for this design takes actually a lot of time. So for this design, it actually takes more than an hour. But even synthesis for this design takes a long time. It takes 14 minutes to synthesize this design. Lightning Sim running in parallel can actually finish in 9 minutes. So that's 5 minutes faster than the synthesis takes. And this is basically what I was saying earlier about how RTL generation can take a long time. So Lightning Sim not having to rely on RTL generation can actually speed things up quite a bit. So, right. And then one quick thing to note about this one. So this example, as I mentioned, uses data flow, and it uses these FIFO streams as part of the design. And you can see here that there are a bunch of streams here, and there's like one here where you can see this like depth of 200. So you can actually see that if I update this, let's say I update this to, wrong one, I'll just set that back. But if I update this to, let's say, 49, you can see how quickly Lightning Sim determines that the design is now deadlocked, right? So it's actually very quick to update these depths and get new estimates for the latency, or figure out if your design is going to deadlock. So now I think we can be finished with this project, and I'm going to go ahead and quickly try and run through the last example, which is basically using the Python API and also doing design space exploration of these FIFO depths with the Python API. So I have oh geez, I hope this doesn't take too long. I have a Jupyter notebook for you. If y'all are familiar with Jupyter, it can be great for having like code in cells, and then you can execute codes like this code like one cell at a time. So it's great for like tutorials for Python APIs and such. So that's why I'm using it here. So go ahead and do this conda install command, conda install -y -c conda forge Jupyter Lab, and this will install the Jupyter Lab interface to go through this walkthrough. All right, solve the environment. Hoping this one doesn't take as long as the last one. Also, I'm going to close this tab in the meantime. You can also go ahead and close Vitis HLS for now. We're actually not going to use the Vitis HLS UI for this last example. I've already pre-synthesized the design, so we're just going to use the Python interface. Okay, great. So now we have the Jupyter Lab interface installed. So what I'm going to do now is I'm going to change directory into the example 5 directory. So go to cd examples example-5 and run Jupyter with a Y lab as 2 words. And what this will do, it should launch our browser. All right, and I'm going to go ahead and open this notebook. So go ahead and double-click the example5.ipynb notebook here on the left in the file pane, and we're just going to go through this example. Hopefully hopefully won't take too much time. I'm going to go ahead and full screen this so that we have more space to work with. All right. So now, so the first thing is I'm just going to import a few libraries, including a couple of classes from Lightning Sim, the solution, runner, and runner step class. So the first thing that you want to do is construct a solution. So this is basically the same as passing in the solution directory on the command line. You just pass in a pathlib object corresponding to the solution that you want to use. And then what you do is you pass this to the runner class. The runner class is what's responsible for compiling the LLVM and getting the execution trace. And it also does a couple of the trace analysis steps. It does steps A through D within this diagram. So it makes the LLVM IR traceable, executable, traceable, and then does a little bit of the trace parsing and resolving dynamic schedule. So you can do runner equals runner and pass in the solution. And by default, this won't actually output anything as it runs. So I'm going to go ahead and add some hooks to print progress information. And then you simply do await runner.run. So this is using like a Python's async await features to, so you will need either to call it as await runner.run, or if you're doing it from a non-async function, then you have to do async io.run and then pass in the runner.run object. All right, so it looks like that worked. So we can see we got this resolved trace object at the other end, and this has a bunch of properties. The ones that are, I'm not going to go through these in too much detail, but the one that's most important here is what this compiled property that is a compiled simulation object that is basically almost the actual simulation results, but it doesn't actually have the actual cycle count yet. So it's basically compiled into a graph. It compiles the simulation into a graph, and then this params property, which is of type simulation parameters, includes some of the parameters that we need to actually resolve that graph into actual cycle counts. So the parameters include the FIFO depths and the AXI delays for any AXI interfaces on the at the top level. So the initial value that's provided in trace.params are whatever you provide in the HLS design. So if you just do trace.compile.execute, trace.params, you'll actually get the number of cycles for this design. And so you'll get the actual, you'll get a simulation object, which includes both the number of cycles for each module in the design, and it includes like basically a module hierarchy. So you start with top module, and you can print the name, start, end, and submodules of each one. It also includes some information that I won't go into on like when FIFO reads writes happen, as well as AXI reads and writes. But you can basically traverse down from the top module and see the cycle counts of each module in the design. So basically just showing what the overview tab does in the web UI. All right, now what you can do is basically, if you want, in the web UI, you can change one of the FIFO depths and rerun it will rerun the simulation automatically in a few milliseconds. You can do the same thing here. So in this example, I'm finding a FIFO in this design that's named channel, and I'm setting its depth to 1024. So I find that FIFO, I set its depth to 1024, and I just do trace.compile.execute with the new parameters, and you will see that it gives me new simulation results almost immediately. So, and then this is a more interesting example if you are trying to do design space exploration to figure out what the best FIFO depths are. So basically what it will do is it will give you basically a design space for the FIFO that, and it will run the simulation on each of those points. And so basically you can see based on this DSA result that if you set the depth to 2, it will take 0 VRAM resources and take 114,000 cycles. If you set it to like 4,096, it will take 98,000 cycles, but use 57 VRAMs. And if you keep increasing the depth, it continues to increase the VRAM usage. But at some point, the cycle count plateaus and becomes 90,000 cycles rather than decreasing any further. And you'll notice that, that this is skipping some values, obviously, so it's skipping anything like between 2 and 1024, skipping anything between 1024 and 2048. The reason for that is actually because based on the way that Vitis HOS synthesizes these FIFOs, there's actually no benefit in choosing a depth value outside of these points, because if you choose something like 1023, it uses the same number of resources but takes slightly longer than 1024. If you set it to 1025, it takes the same number of resources as 2048 but takes significantly longer than just using a depth of 2048. So you can use this for design space exploration using FIFO depths, and you also can see how you can use Lightning Sim programmatically to get latency of just any design, regardless of whether you're doing design space exploration or not. All right, so that's this example. So once you're finished playing around with this, you can go ahead and click on File, Shut Down, and it will shut down Jupyter Lab. Leave, okay. And, okay, I think that doesn't matter. But yeah, that's Lightning Sim's Python API. So congratulations on reaching the end of this part of the tutorial. You're now a Lightning Sim expert. Obviously, there were a couple of examples that we missed. If you wanted to go back and do those on your own time, please feel free. It's basically just an example that shows when HOS synthesis doesn't actually know the cycle count, how Lightning Sim can help there. And similarly, there's one that shows like an example of a design that deadlocks, so and how to fix that deadlock using the using some of the information provided by Lightning Sim. So I do recommend that you go through those on your own time if you are interested. But for now, I think that's it for the Lightning Sim part of the tutorial. I don't think we have time for a break. Okay, we'll take a 10-minute break then, and then after we return from the break, let's say we return at 1:57. Yeah, we'll return at 1:57, and we'll move on to the real probe tutorial, where Jiho is going to take everything I said about simulation and completely destroy it. No, I'm kidding. But
Okay. I would like to do a quick summarization. Feel free to go if you have to. It's just a very quick thing that we're going to take a 10-minute break, and then we will switch from simulation to onboard prototyping and to help you to figure out why your RPG design is slowing down or how accurate CoSim is. So Rishal said, hey, Lightning Sim is really cool. It gives you a very accurate CoSim. And then we will say, actually, CoSim is not reliable. So please come back at 2. And during the break, if you have any questions, feel free to reach out to us. And also, don't worry about if you're missing anything, this tutorial is recorded and will be published later after this tutorial. Right now, it's on YouTube stream. So it will be recorded. All right, thank you.
you didn't update it after you sent it to Kelly, right?
No, I visualize.
Yeah.
Is this live streaming right now?
I think so.
Can I ask you something? I'll ask you offline later.
Is it working? I think it is.
I think so. Where is the report? After this, oh, okay.
Yeah. So just go there.
Let me,
Do you check anything?
I want to change the setup.
Oh, I see.
Browse by individual.
Gotcha.
Yeah. Yeah.
Right.
Because
Right, because you have it side by side. I remember. Yeah.
also, where is this one is right?
Yep.
Okay. If I want to see the CoSim results, like the CoSim report, should I just open with the file server in here, or should I just like use the terminal?
The terminal's probably faster. Or you're saying file manager? Yeah, that's fine. I think.
Okay.
schedule.
I like my certification. Use FPGA designs. Like our biggest problem is we have 2 FPGA engineers and a whole team of firmware engineers. So if you think like this is something useful in trying to hey, like you're a firmware engineer, you don't need to know Verilog. We have all these tools at our disposal. You can use metal synthesis. And when I say simple design, it's a CPL management, right? Square waves, image, like little things like that. We have some FPGAs that do motor control. Would you say that this is something that could work with for simpler designs, not just big designs?
I mean, I think so. I think you're probably using what's going to happen in each individual site. So if it's simple enough, you can write your line.
That's the thing is like if it's a smaller project, like for myself, we can do everything pretty quickly. But then what if we I don't know want to expand a little bit?
Then for sure, I think Iowa synthesis.
Right.
Yeah. So because the great advantage of Iowa synthesis is that you're abstracting the low level. Yeah, exactly. So you just need to rewrite C code. I mean, writing C code is a bit of an oversimplification because
it's like modified.
Right. But it's still I think a great prototyping tool, and especially if you one of the goals of Lightning Sim is to make it just basically one of the things that's basically the goal of my PhD project in general, and actually if you want to provide PhD forum on
That's right.
then we have to tell you more, is making the hardware development ecosystem more like software development in terms of how easy the developer experience is, how easy it is to test, evaluate, debug, and iterate on designs. So I think Lightning Sim is a great step in that direction, on top of how so I'm hoping that this is basically promoting, helping people.
I mean, that's the issue we're running into, right? Is we're getting to a point where we're slowly seeing, oh crap, maybe we need to use more FPGAs in our designs, but nobody knows Verilog.
Right.
Like I worked on a design and I showed our senior firmware engineer. I'm like, hey, can you take a look at my code? He's like, I've never seen Verilog code. Oh crap, what am I gonna do?
The learning curve is a steep for Verilog. For HOS, you can start off. Eventually, if you want to do like complex things with like HOS streams and those all that, then there is a market. But like it's a lot easier to do very retention. So
Interesting. Awesome. Thanks. Yeah. I look forward to this talk.
I have a design based exploration. Okay. Have you looked into or do you implement the ability to do design based exploration right now?
So right now, the answer is no. The reason is that that the key thing with FIFO dumps is that changing the depth does not actually affect the scheduling or RTL of your design. So if you change the depth, all that does is change the stalls. So anything else, like let's say you want to partition an array, right, and you change the resolution factor, that's going to result in completely different scheduling because maybe you're going to have like conflicting accesses to server banks and things like that. So basically, the HOS tool is going to have to reschedule all of that. So that's the reason that we focus on FIFO dumps, because that's one thing that first of all, existing tools don't really do very well, and second, that is feasible to do just by recalculating stalls using our approach.
Yeah. Okay. Because one thing I was thinking about is you could create triggers in this as well as the kernel. Where is that possible?
So actually, yes, and so actually one of my colleagues in my lab has like a Python library that I think he calls it VHLS. I'm not sure if it's yet, but it will be soon. That you can like go write HLS from Python. And so with that, you absolutely could integrate that with like you just have like a one-step thing to resynthesize and rerun it.
Yeah, because it's interesting to leverage the ability to reduce the number of synthesis jobs with also sort of creating synthetic jobs.
Absolutely. Yeah, that's definitely something that should be relatively actually I would be
yeah, it's very useful. Definitely counter so see RTL simulation.
Well, that's the debate, right? But it can't
Sure, that's a long-lasting discussion.
Right. Sure.
Okay, we are going to start with the next tutorial, which is Real Probe. Hello everyone, my name is Jiho Kim, and I'm a first-year PhD student in Shark Lab at Georgia Tech under supervision of Dr. Kelly Howe. I'm going to talk about the Real Probe tutorial, which is the part 2 of Understanding Your FPGA Design Better tutorial. Real Probe is going to be a tool for the onboard profiling, and let's start. Real Probe tutorial schedule is as below. So we finished the Lightning Sim tutorial for the rapid simulation. And for the Real Probe tutorial, I'm going to first talk about the Real Probe for the first 10 minutes, and then we are going to go through hands-on experiments and also my pre-run demonstration that we can actually see the different results from CoSim, simulated result, and onboard results. So this is our outline, and I'm going to start with the talking about background and motivation. So I will briefly recap the Lightning Sim and the Vitis HLS development flow. So if we have a HLS source code, we can input the HLS source code to the Vitis HLS, and then we can directly get the RTL. So yes, HLS is a very powerful tool. And inside the Vitis HLS, we are going through the C simulation, and then C synthesis, and then co-simulation. We can get the report from each stage, but most accurate result is from the co-simulation, as Richard mentioned. And then if we put the Lightning Sim and then replace the co-sim with the Lightning Sim, we can get the rapid simulation now. So what is next after the simulation? We have to think about our eventual goal of our FPGA design, is that we have to deploy the FPGA design on the actual hardware, and then we have to measure the onboard performance, not the simulated results. So I will talk about the whole FPGA design flow with HLS, and I'm going to use a Vitis HLS and Vivado flow with it. This is very realistic flow, and so if I was a designer and then I'm using the Vitis HLS, I'm gonna start with the HLS source code, and then I'm going to go to C simulation and then check my code's functionality, and then go back and forth to check actually run without any error. And then now we can start to explore the design with different pragma configuration to optimize our design. We go C simulation and then go C synthesis and then go co-simulation. And for the co-simulation, we can both check the functionality of our RTL output, but also the performance simulated result. So if we don't like the simulated performance and we have a very strict constraint, we have to optimize our design more and more. And then we can start to use different configurations of pragma so that we can optimize our design. So this is usually going back and forth again and again. Even though this is very rapidly simulated with the Lightning Sim, this takes quite a lot of time, and we spend a lot of time optimizing our design based on the simulated estimated results. And after that, we get the RTL results from that, and then we have to go through the Vivado design flow, which is making the RTL to the IP and then integrate the IP to the block design and then system level. And then we go through the synthesis and then place and route and then bitstream generation flow. After that, we get the bitstream, and then we can now program the FPGA, and then we can do the FPGA programming. So finally, we got the on-FPGA result after all this process. But is it done? Is it almost done with the FPGA design? It's actually not. So we saw that cycle difference between simulated and on-FPGA results are very large than we expected. It has almost double difference, even with very simple benchmark. So the left side is only the accumulation benchmark, and then the right side is just a matrix multiplication with the 64/64 size of the matrix. We could see that C synthesis is not, CoSim is more accurate than C synthesis. But however, still CoSim has 100% off from the onboard performance. And then now we have to concern about what is the actual onboard result. But how do we get the on-FPGA cycles? So the current on-FPGA performance profiling tool provided by Xilinx, we have a Xilinx Vitis analyzer. With the Xilinx Vitis analyzer, we can have the on-FPGA performance, but only about the end-to-end cycle. So even though we know the actual cycle is different with onboard and the CoSim result, we cannot get the information of what module is making the difference and what can we do better. So another way to look at our on-FPGA result is using the integrated logic analyzer, which is called ILA more. And this is for monitoring internal signals. This is mostly used for the RTL designers so that they can probe the signal inside. But the problem is that it has to go through the RTL file inspection. We have to check the signals, what we actually have to see which signals are making this, showing the cycles from the end to end, so that because the HLS benefit is that we don't have to look into the RTL. But eventually, if you want to see the onboard result, we then have to look into the RTL, which is diminishing the HLS benefit. Also, it needs a lot of users' manual effort because it has a maximum depth we can see. And then most of the design we have is a multiple thousand cycles, but the maximum depth of ILA has a very limited range, so that we have to go through multiple cycles, checking each signals and then trigger which signal to be probed. And then this takes a lot of effort from the user. And also in the first figure, we can see that ILA is using a lot of BRAM usage compared to the real probe I am going to talk about. Using BRAM usage is very critical for our actual designs because we usually target for maximum BRAM usage for our implemented design. And then if you want to use the ILA on top of it, it's usually not fitted in the FPGA so that we cannot use the ILA with the big design we have. So it has a very high VRAM overhead, and also it needs a lot of signal inspection and the cumbersome process we have to go through. So the motivation of our real probe, to summarize, is that we found the discrepancy between simulated and on-FPGA performance. And this is really critical because the bottleneck functions can be changed in the co-simulated result and the on-FPGA result. So even though we try hard to optimize our design based on the co-sim result, we eventually have to go through the on-FPGA and then go back to it again, and then we cannot blame co-sim anymore. And because we are lack of the practical on-FPGA performance profiling tool, it's either restricted to end-to-end latency or diminishing the HLS benefit. So what we did is to just make our own tool that we can probe the on-FPGA performance. So the features of Real Probe includes it's fully automated for zero manual effort from the user. So I modified the front end of Vitis HLS Clang LLVM so that they can recognize our custom pragma, which is pragma HLS Real Probe. And then this makes the function fully automated onboard profiled onto the stage of where we can check the performance on onboard. And it's seamlessly integrated into FPGA design flow, so we don't have to make more process of the using Real Probe. For the Vitis HLS and the Vivado flow, we can just use the Vitis same flow, original same flow, and then Vivado flow. And then Real Probe is integrated into those design flow, so we don't have to install any tool or any other process. And the good thing about Real Probe is that it has no software dependency to other tools. So one of the frustration that I had with coding and working on the FPGA stuff is that when we want to use a tool, and then we found it a really good tool on the GitHub, and then we download it. And then we always see the error saying, oh, Python version doesn't match. So I wanted to get rid of those frustration of integrating the tool to your design, to any design. So I only use the Tickle script to code everything. And the Tickle script interpreter is in the Vitis HLS. So if you have the Vitis HLS installed and Vivado installed, you can just run it thoroughly even without installing anything. It's informative and scalable compared to the other profiling tools. It is showing the iterations, how many iterations each function had, and each cycle per iteration. And we checked with the 26 benchmarks so far, and then it has a 100% accuracy. We cross-checked this with the ILA so that we can actually know if the Real Probe is showing the right result. And then it has an average 5.7% of runtime and 0% VRAM overhead. For the runtime, ILA usually have 70% to 80% runtime overhead, so we reduced the runtime a lot for the Real Probe. So how I implemented Real Probe is, I will explain about how did I implement the Real Probe. So this is the original flow of the HLS source code to FPGA deployment. So when user insert the Real Probe pragma, we can just see the result with the Real Probe function we support. So inside, I modified the custom Clang and LLVM, and then we can insert our custom pragma, and then the LLVM Clang library will recognize our custom pragma and then generate the metadata according to it. And then we put, when we run the sysynthesis, we are referring to the library that we compiled with the Real Probe pragma, and then we use the metadata to check where is the Real Probe at, where the user wants to probe, and then we generate the module hierarchy graph, and then CRTL function mapping table so that user can know which modules are mapped to the which functions. And then we have to extract the control signals. So Vitis HLS generated IP usually have the AP start and AP done signals inside, so that each module has a certain signals toggling when they're starting, and then when they're done, when they're toggled again. So we are extracting that control signals from bottom to the top where user want to probe, and then we are extracting every function's control signals user specified. And then we automatically generate the IP of RealProbe, and it's based on very simple counter based, so that it can have a less resource overhead. And for next, so after you generate the RealProbe IP, we have to integrate into the previous system where we have to connect the control signals from the Vitis HLS generated IP to the RealProbe, and then we have to give it to the CP processor that we can read the result of RealProbe. And then finally, we get the results from the RealProbe. We can either get the result from the DRAM or registers we used for the RealProbe IP. And these flows are fully automated in the back end, so users don't have to care anything about it, but only just inserting the Pragma HLS RealProbe. So what users see is that just if they have the code according to, like for example, if they have a code like this, user wants to probe where is the bottleneck function and what is the cycle for each function. User can just insert the Pragma HLS RealProbe on below of the compute, and then the result of RealProbe will be after the fully automated RealProbe flow, and then we are getting those right RealProbe profiling result. So we are going to go through the hands-on examples. Because we have the time limit and we have some limitation of our environment core speed, we will run one example. And we are going to provide more complex example on GitHub later. So what I'm going to do with this hands-on example is to show the pre-ran matrix multiplication demonstration. So before this tutorial, I ran the matrix multiplication with RealProbe and then extract the cosim result and then the onboard result. So we can see the actual cycle difference with this example. And then matrix multiplication is very simple single top level function. So it's only for the start and understand the basic of the RealProbe. So for our example, we are going to use the custom nested function example, which is there's multiple functions nested to each other, and we are going to probe each function cycles with the RealProbe. So for the environment setup, we are going to still use the environment setup we used from the Lightning Sim. And then I'm going to set up my environment here. So we can close the terminal now from the Lightning Sim, and then we can open one new terminal. And then for RealProbe, we are going to use the Vitis Vivado version 2023.1 for this tutorial. So you have to set up the version of Vitis as with the below code. So I'm going to type this, and then we can see that we are configured with the 2023.1 version of Vitis, and then 2023.1 for the Vivado as well. So now we are going to download the RealProbe from the GitHub directly, and then I'm going to just type the git clone and then type the address website. It will take approximately 2 minutes to download. Oh, you have to put the .git at the end of the repository. So I'm going to type in like this. Oh, yeah, thank you. So while it's downloading, I'm going to briefly talk about the tutorial directory path setup. So what we are going to use for this tutorial is that we are going to run the example 3, the nested function example, and then
This download and all the commands are also available on the
realpro-doc.
the README doc. So if you cannot see it clearly from the slide from the presentation, just open the browser and you can copy that command.
Same as the like
Yeah.
doc one, but it's realpro instead.
Yes.
So while downloading GitHub, so for the examples, I prepared the HLS source code, which is the C and C++ files that we want to use. And then for RealPro, you have to prepare the hls.tcl script, which is just the tcl script running the Vitis HLS. In the RealPro folder, this is where the core RealPro functionality is. So every tcl script that RealPro is running is in the RealPro folder. And then we are going to just copy the makefile from the RealPro folder for any project you want to run. And then you can just run the RealPro afterwards. And for the HLS build, is the build file that after I modified the Clang LLVM, including the RealPro. So this is only for the referencing the library. And for the LLVM project is the modified Clang LLVM for RealPro is open source with this folder. So if you want to modify the RealPro pragma, or if you want to make your custom pragma, you can refer to the LLVM project folder so that you can make your own custom pragma or be a developer of RealPro and then make the RealPro better. Can you raise your hand if you are downloading the RealPro right now? Okay, sounds good. So the reason that it takes a long time is because of the HLS build and LLVM project folder. So RealPro itself doesn't really has memory, or it doesn't have many files to download. It's just because of the library file that we have to download. So my file is downloaded, but I'm going to wait a little bit more for the audiences who's trying the RealPro right now. And yeah. Can you raise your hand if you're still waiting for RealPro to be downloaded? Okay. No worries. Sorry? Oh, okay. So what we are going to do is to go inside the example folder. So I'm gonna type cd examples and the example 3. We are going to run the example 3. Oh, sorry. I will go into the real pro first, and
These are
then.
not the same examples from the home directory, so make sure you CD into real probe.
Oh, yeah. First cd real probe, and then I will go to the examples folder, and then go to example number 3. So in here, we can see the example.cpp file and then hls.tcl-script. So in the example CPP file, we have both test bench and the source code ready, and the HLS tcl script is provided. So we have to run the real pro from now, but because of the system setup we did has only 4 cores can run right now, and it takes quite a long time to just run the Vivado itself. So it's gonna take around 20 minutes. So we are going to run it now, and then we are going to go through the other information about RealPro. So what I'm going to do is to just write make RealPro, and then this will automatically recognize the progma inside, which folder is marked with the HLS RealPro progma, and then it's going to go through all the process until the bitstream generation and the FPGA FPGA programming. So I'm gonna run make RealPro. Oh, so I have to copy the make file from the RealPro. So I'm going to copy the RealPro make file to here, example folder, and then I'm going to run the make RealPro. And then we can wait for it to be done. So just to be note, RealPro itself doesn't take a long time. As I mentioned earlier, it only takes 5% overhead from the original design implementation flow, but because our system has a little bit slow cores running right now, so it just originally the Vivado design itself takes 19 minutes to run. So while we're running the RealPro in the right side, I'm going to talk about the mode that how can we run the RealPro. So currently RealPro support 3 modes, which is first is the original FPGA design flow, and the second one is the RealPro integrated FPGA design flow. And the third one is the RealPro. After we run the RealPro, you don't have to go back all the way to the C source code level, and then you can just run this make function and then the new function that you want to probe, so that we can just check after the VIDIS HL generation from the RTL level. We can change the RealPro IP, which function we want to probe, and then we change the counter numbers inside, and then we can only run the incremental synthesis and implementation because we only change the RealPro IP after. So for original FPGA design flow, we can only just run make base. So make base is running the original design flow from the HLS source code to generation of bitstream. So you can use the RealPro with the integrated RealPro as well, but also you can just use the RealPro tool for your FPGA design flow automation flow, so that you can just put your HLS source code and then the HLS tcl script inside, and then you can just directly get the bitstream out of it. You don't have to go through the Vivado process. And for RealPro integrated FPGA design flow, as I explained earlier, it's going to go through from the HLS source code to the bitstream generation level as well. And it generates the IPython file so that we can directly run the script on the FPGA board, where we are going to demonstrate later. And for the RealPro changing probing function, so on the base figure, we can see that system integration includes Zinc system and then the HLS generated IP and the RealPro. And then those two files cores are not going to be changed, and only the RealPro IP is going to be changed. So this is going through the incremental synthesis and implementation flow. So even though you change the function that you want to probe, it doesn't take a long time that you have to go through all the steps ahead. So this is just the comment that you have to write for running the original design-based flow, real probe-based flow, and then the function change flow. So this is very simple and very intuitive so that you can just run with the makefile script. So what I'm going to show while we are running the real probe on the back end, the matrix multiplication example from the Dr. Kessner, where Rishabh also mentioned about it. So Rishabh showed the matrix multiplication simulation on CoSim with the Lightning Sim, CoSim and the Lightning Sim. And so for our example that we provide on the GitHub is that we all provided the HLS source code and then test bench files and then data files and also HLS tickle script. So in matrix multiplication inside, I marked the top function, which is, this is only the single top function, so I marked the pragma HLS real probe on the bottom of all the other pragma. And then in the HLS tickle script, so we have to prepare the HLS tickle script to run the real probe, and it's basically what we used to do without the real probe. So to run the Vitis HLS in the tickle script, we have to define the solution name, project name, and the target device. And we have to set up the project, open project, and then set the top function, which we are going to tell the Vitis, this is the top function that I want to make it as an RTL. And we have to set the device that we want to target the FPGA. And for the run simulation and synthesis, I am running the comment right now, but for running real probe, CSIM design, which is the C simulation, and also the CoSIM design doesn't have to be included, but because I am going to show the difference between the CoSIM and real probe, I have included this comment inside. So we are going to use the FPGA board after we're done with the make real probe. So for the FPGA setup, we have to open the on-demand as we did earlier. And then we are going to click the pink C2 FPGA and then click the Jupyter notebook, and then we can connect to the FPGA board. After running the Jupyter notebook, we are going to launch with the default settings, and then it takes a little bit of time, and then when it turns into running from queue, we can connect to the Jupyter. While we are setting up the environment, I'm going to show you the pre-ran matrix multiplication example with the cycle difference between real probe and the CoSIM. So I'm also going to launch the Pink Z2 FPGA Jupyter notebook with the default setting. For the make real probe, for the example 3, it's waiting for implementation to be done. And then we can, I will show you the CoSIM result from the matrix multiplication with the 64/64 size. So on the CoSIM result, we can see that we have only one reported cycles, which is only the end-to-end report. So if we actually want to see how many cycles it takes for each function on CoSIM as well, we have to trace all the data, all the signals, and then we have to dump it, and then we have to see the waveform to see how many cycles it took in the CoSIM. So beside of that, this shows 50K cycles in the CoSIM result. And then we are going to launch the Jupyter notebook that I pre-ran, and we are going to see how many cycles it actually took on FPGA. So I'm going to just go into the pre-ran example I ran. And after running the real probe, you will get the FPGA folder, which is ready to go to run the FPGA. So it has the bitstream generated file, hardware handoff file, and then this FPGA.python file is automatically generated to run your IP and also the real probe output. So for example, with this matrix multiplication example, this has the library import part that we have to run. We have to use for the run. And then we are going to load the overlay. And then we specify the dimension with the code that you wrote on the C code. And we automatically map the physical address that you assigned in the Vivado so that we can just run directly to run your IP. If you want to verify your functional correctness, you can just type your C code, type your Python code here. For example, this is matrix multiplication, so you can just type in the matrix multiplication, which will result the same output, and then you can check the correctness. And for the real probe output, we are going to just run this function, and then we can see this clock cycles is actually 102K in the onboard, which is a 104% different from the COSIM result. So that it means that we cannot rely on the COSIM results anymore, and then we actually have to see the onboard result, and we have to have the ability to know what is actually going on the FPGA. So we are still waiting for the real probe to be done. So we have 104% difference, and we are going to see the nested loop function after the make real probe is done. And then we can see the each function's latency cycle count with that example.
I have a question.
Yep.
What if your functions or your loops have variable durations based on like the data that's input? Do you have the ability to track counters, or say for example, a function sometimes takes this long, sometimes it might take this long?
Yeah. So the question was, if we have a different number of iterations for each run, can real probe can track the yes? So because real probe is actually tracking the signals of onboard, so we can see the actual cycles on board with the different input. Yeah.
What if a particular function, for example, if you call it multiple times, has different latencies? During one initiation of the accelerator, maybe a function takes some number of cycles one time and some number of cycles another time. You have the ability to measure that.
Yes, so we are offering the information of the iterations of each function and how many cycles it takes for each iteration. So we can check, for example, like sorting example, we have the benchmark ren for the sorting example. So if we run like different input, they have a different cycles for each iterations. One interesting thing in the real probe is that so we have a benchmark of Rosetta from Dr. Zhu Zhang from the Cornell University, which is the realistic applications for the HLS. So we tried their benchmarks on the real probe, and then especially for digit recognition, for training the digit recognition, the actual DNN accelerator, it took more than 30 hours for the COSIM simulation. But actually, when we just use the real probe to track the onboard cycle inside, it takes 10 minutes to finish the Vivado implementation, and we can actually see the onboard profiling result. So if we are only using COSIM for the performance measurement that we want to optimize the design based on that, RealProbe can actually replace the COSIM on those specific cases where your model is really, really big and your model takes a long for the COSIM. You can just implement and then just check the RealProbe, and then you can check the functionality on the onboard too. So RealProbe can work on the actual onboard, but also for your COSIM or replacing the performance measurement. I think it needs more time to finish the implementation, so feel free to go to the bathroom and then take a break. Oh, it's writing the bits.
don't need different strategies, right?
Sorry?
You don't need different strategies, right? It's just one.
Yeah,
one
yeah,
sign.
just one time, yeah.
How much overhead is real pro? Like big and lot usage, five usage, huh?
Yeah, for the resource overhead oh. Oh. Um,
Okay, understand.
yeah. So for RealPro, for LUTs, we are using 39.9% overhead from the original design, and we are using 37% for registers and 0% VRAM.
You have a clock drop on ILA does, so like
Oh, the time,
Like the, they have I believe you have to have the same synchronous, but have the clock be synchronous with ILA, so the same page, so it goes all.
we, I, th- because we are using the same clock signals for now, I think I think it has to run with the same clock because we are probing their signals to our signals. So yeah, so we are using the same clock signals. Yeah. Sorry. Yeah. Sorry. Can, oh, the question is what Vivado version it can support. So technically, this RealPro can be run on any version of Vitis and Vivado, but the thing is that you have to have a same matching version with Vitis and Vivado, and also Vitis HLS. Xilinx is open sourcing their front end, and we are modifying them to recognize our custom pragma, and they have their versions of open sourcing the front end. So three thing have to have a same version with Vivado, Vitis, and their open sourced LLVM Clang library. And for those versions, we can support 2022.1, 2023.1, 2023.2, because they started open sourcing it from 2021, as I remember correctly.
So when you're comparing with the ILA, is that the Vivado?
Yes, that's right. So we can make the option for RealPro to be configured into the VRAM or registers. So we are planning to make a extend RealPro to have multiple options that designers can choose. But for now, I targeted RealPro to not use any VRAM resources just in case we want to have a large design files. Yeah.
In terms of utilization, sorry if this has been asked and answered, but is it, what kind of granularity is there? So, I mean, what you showed first was it like, there's just from a crowd, like, it looked like kind of a blanket pragma
Yeah.
in your HLS file.
Yeah.
Just like, use RealPro.
Yeah.
And then that presumably installed all of the tooling to export all of the control signals that RealPro might need in order to probe this or that or whatever functions internally.
Yeah.
And then later on in the process, it's actually installed to look at the specific things you want, right?
Yes.
So I guess I'm curious, like, how much of this additional resource overhead is associated with that original, like, sort of blanket HLS level tooling, and how much is associated with, like, the things that the developer has more control over?
I see. So the question is that if we, how much range of, how much freedom does RealPro have to make the designers configure their, design resource? Yeah.
Limit the resource utilization,
I
just
see.
that
Yeah.
Utilization's very tight.
Yeah.
You don't have a lot of room to put anything in.
Yeah. So currently, what RealProbe does is that if they have the same function iterated multiple times, it is dumping the result to the DRAM so that it doesn't include many DRAM registers resource usage so far. But because, as you mentioned, there are many multiple big designs out there, so we have a limited number of functions to 30 currently. But we plan to make it to be more user-friendly so the user can specify how many functions that user want to see. I am thinking of making the comparison between COSIM result and the RealProbe result, and then if we can show the users the top 30 functions that have most difference between the COSIM and RealProbe result.
Just a little follow-up.
Yeah.
So maybe this would be a better way to ask my question. How much overhead is contained in expanding the size of the HLS IP that's been generated using the RealProbe tools, and how much of the overhead is contained within the additional IP blocks that get generated to process the outputs from that? I guess is sort of my. Is that a sensible question? Or is that just convey a misunderstanding of what's going on?
Sorry, I think I didn't understand your
So
question.
what I'm imagining based on your description earlier is that when you're using RealProbe, it's installing some extra features into the HLS IP that's being constructed on the block diagram level. And then later on in the FITIS, building process, it's constructing additional extra IP that takes the outputs from that additional stuff.
Yeah.
And, computes, summarizes, counts, whatever it's doing, delivering that output via probably AXI to the processor.
Yeah.
So my question was, how much of the additional overhead is contained in that, the expansion of the HLS block versus the custom processing block that analyzes that stuff?
I see. So the question is that if compared to the original Vitis HLS generated IP and the Vitis HLS IP with integrated RealProbe, how much difference those IP have? Right.
Thank you for the question, by the way. I think it's clear, it's better to show this figure that on the left side is the HLS generated IP, and on the right side is the RealProbe IP.
Yeah.
And what we have to modify for the HLS generated IP is just to externalize some of those signals, just some wires.
Okay.
And then that's basically a zero overhead.
Free,
Yeah, it's free. And then almost all the overhead comes from this RealProbe IP. Does that make sense?
Yep.
Thank you for the question. I will check if our RealProbe is done. So yeah, it's done. So it has the result in example 3. So I will go to the example 3. And we now have the FPGA folder ready. So if we go into the FPGA, we have the bitstream generated and the hardware handoff generated. And we also have the IPython file generated. So we just can run this code. And then if you want to check your correctness of your functionality, you can check with the Python function. And then after we run the RealProbe, we can see now each kernel's latency cycles we have. So I will show you the original function, what it looks like. So for the example file, so inside the main, we have an example function here, and then inside the example function, we have the example 2 inside, and then inside the example 2, we have the example 3 function inside. So I wanted to show the nested function example, and we get the output of the cycle count for each function after the make RealProbe is done. So this is a little bit simplified version to make it run faster. But you can check more complicated, complex designs after this tutorial. I will upload it, and then it will include a lot of details like iterations, how many cycles in each iteration takes. So feel free to reach out to me if you have any question or if you have any suggestions to make the real proof better. So I think our time is done. So thank you so much for attending our tutorial, and I hope it helps you to run the FPGA design in the future. Thank you so much.
Yeah, I think that closes this section. So I didn't prepare any summarization slides, my fault. But hopefully we got to enough information about Lightning Sim and RealProbe. Tell me it's cool. They're cool? Okay, I'm happy. Thank you for saying that, even though if you're like. So a brief summarize, Lightning Sim gives you a super fast code simulation, speed up, right? And it's easy to use. You have a predefined HLS design. It's synthesized, and you just need to evoke RealProbe and point, sorry, not RealProbe, evoke Lightning Sim and point Lightning Sim to the pre-synthesized design, right? And it works. You don't need to rewrite your original HLS design. That's Lightning Sim, and then for RealProbe, it's simple. Just one pragma HLS RealProbe, and there you go. Just deploy that on FPGA and see if it matches. So, highly recommend for high-level synthesis, highly recommending for Lightning Sim plus RealProbe. And this is final thing we want to say that now you have no excuse telling your boss my code is simulating. I'm the boss, I know, I'm happy now. So thank you all for attending, and all these things will be, this recording will be released, and all the materials will be online, and we have all the open source code, all the GitHub, everything is ready. And if you have any questions, reach out to any of us. We should be super happy to help. All right, thank you so very much again, and have fun. Go have fun with the HLS and FPGA world. It's a better world now.